Now it's my turn, right? I'm telling you, I did everything I was supposed to do over and
All right, kids.
over again. Finally got fed
Let's
up.
figure this out.
Wouldn't let me move.
Let's figure this out.
I go, look, I did it just like this. And the
Let's
character
take a
knows
look
better.
at that and make sure we know what it's telling us. And then we're going to introduce a new idea called average rate of change. And I like this because we're going to be getting into the idea of the word average, which is where the kind of the back half of the course I wanted to go on average. The word average, I want to get us comfortable with that. So forget the graph for just a moment. Forget the graph for just a moment and go back to your quadratic screen, the main screen of your calculator. I just hit second mode to quit out to the home screen. Now a linear model, as we saw before, looks like y equals ax plus b, where a is the slope and b is the y-intercept. A quadratic model now adds a third term, and it has to. It has to because now you have a potential. They don't all have to, but in general there's going to be three terms because you have a squared x term, a linear x term, and also a constant term. And this is probably old news to you. Quadratic models look like this. Y equals ax squared plus bx plus c. And some of this is going to be a bit of a review for you. You've seen this before. You've seen this before. But maybe you don't remember it, and that's okay too. That's okay too. This guy right here is called the quadratic term. Just conversationally we call it that. Why is that the quadratic term?
That's an exponent.
Because the exponent on x is 2. The exponent on x is 2. Exactly. B, the bx term is just called the linear term.
So if the exponent was other than 2, it would no longer be quadratic?
It would be quadratic. If the highest exponent is other than 2. So if it was x cubed, if it was 1.2x cubed plus, it would be cubic. It wouldn't be quadratic anymore.
So
you name a polynomial.
Quadratic is, the quad actually means because it's
This is
raised.
confusing because
Yeah.
what does quad mean? 4
But we have
in
two.
everywhere else except mathematics.
Okay.
Fourth degree polynomials are called quartics, which makes sense because quart means 4 as well. But for some reason, and I don't have a good answer for this, quadratic has stuck with x squared. I don't have a good answer for you there. I wish I did.
You know, some of the things we don't have answers to.
The square has 4 sides. There's only square in 2 of them.
Well, I'm saying, what is that? What about the square?
Well, then a cube would be 8 because a cube has, or 12 actually. It's a 12, but a cube has 8, 12. No, I see what you're saying, Benji. There's no logical connection to it. Because the problem is, if we have to invent a reason that only works in this one particular case, then it's a terrible name. I see what you're doing, and I do the same thing. I tried every possible logical reason as to why it's called that, but it all falls flat. So anyway, we have to make peace with that. And then this guy over here is just called your constant term. This is your constant term. I wish it was called something different. Unfortunately, it's not. So we're stuck. Now the trick with these three things is one of them is still the y-intercept. One of them is still the y-intercept of our model. Which one? Still. Be brave. Be brave, Crystal. Go ahead, say it.
C?
It's gotta be C. This, whatever the constant term is in any polynomial function, has gotta be the y-intercept. And why is that? Why is that? What is the y-intercept? Micah?
Where it's sliced by a knife.
Where it crosses the y-axis. Andrew, I love that. Perfect.
That's where x is 0.
When x is 0, which is equivalent to saying where it crosses the y. So if you take any quadratic equation written in this form, and you let all the x's equal to 0, everything vanishes. That vanishes, and that's left behind. So you can see why this model is only a best fit and not a perfect fit. Because where's the y-intercept of this model? Negative 1.4 what? Give me a unit on that. 1.4 what? That's feet. Because it's crossing the y-axis there. Where should it be crossing if it were a perfect fit? 0, because my bike started at 0.
You don't start the race before you
You're right. I had to move my bike into position, but you guys lined already set go. My bike was at 0 at that point. But it's a best fit curve, not a perfect fit curve. There's all kinds of little inconsistencies in my data. If I were actually doing it in a perfectly controlled environment, I would be much closer to 0, but I probably could never get it exactly to 0 because of the nature of how I was doing it. You guys saw me at the top. You guys at the top saw that sometimes I swayed off course a little bit. It's hard to start from a dead stop in a track stand. It's much easier to gyrate back and forth a little bit to keep the bike up vertical. So we did decently for the conditions that we had. Cool? The other part that's a little bit hard to comprehend is what the other multipliers are. This does get tricky. And so I'm going to conversationally walk you through one of them, and we'll forget about the other one for right now. If you're more interested, I'll be glad to sit with you after class and talk you through it. In linear modeling, what's this guy right here?
Slope.
Slope. What's the slope defined as?
Change in
Change in y or change in x, rise over the run. It's the grade. It's the constant grade. That's perfect. It's exactly what it is. It's exactly what it is. The trick is, in a quadratic, it's also slopey, but it's slopey that's changing, which is why it has acceleration. So slope, and I'm going to write this down once, and I'm going to watch your faces and also watch the noises you make. If I hear dry heat, I'm going to erase it real quick. Slope for a linear model is defined to be y2 minus y1 over x2 minus x1. You remember that?
Yep.
You're like, oh yeah, I remember the algebra class. Here's quote-unquote slope for a quadratic model. It's y2 minus y1, still, over x2 minus x1, the whole thing squared. That's what the slope of a quadratic model actually ends up being. You could do a rate of change in a quadratic model, but it's constantly changing itself. It's not consistent in a quadratic model, which is why when you look at the graph, it's curving. That's what makes the curve curve, is the slope is constantly changing. And sometimes it's becoming less slopey, sometimes it's becoming more slopey. It all depends on what kind of data you have. I'm not saying does that make sense in a way like do you get that, but that explains the change in the graph as to why it's not just a simple straight line. Now, some of you might be feeling a little bit sick right now, and that's okay, because that is a lot to digest, and I don't want to get hung up on it. I don't want to get hung up on it. What I want to do is to describe a way that we can use this idea to talk about that idea right there. No, this is good. Crystal's like, okay, now I'm pissed. Right, now I'm pissed, because now you're not making any sense at all. But here's the deal. How many of you have either seen or been on the receiving end of police officer with the hairdryer?
Yeah, right.
Checking your speed on a highway. You've seen that before. How many of you have noticed as you drive around Bend right now? I see this when I take my son to swimming lessons every week on South Business 97 South. There's now a digital readout that tell you how fast you're going. What they're doing on that sign is exactly what I'm talking about right here. I'm talking about how to measure your speed over a time interval to report back how fast you're going. What they're actually measuring is called instantaneous rate of change. We'll get to that. We might not get to it today. I think we will actually. But we're definitely going to start by going with what's called an average rate of change. An average. So I'm going to make this linear for starters, Crystal, and then we're going to work backwards from that and we're going to make it quadratic via making it linear. Okay. Trust me on this. Trust me on this. This does work. But here's what we have to do first. We're going to get to know our TIs really well today. I'm going to erase. Can I erase most of what's on the board right now? Is that okay? Okay. All right. Let me grab a rag, which I don't think I brought with me. Stop this.